Now, Higher Maths Unit 2, Practice Assessment, Outcome 1. Now, there are 8 marks available in Outcome 1, and in order to pass Outcome 1, you're required to get 5 out of those 8 marks. But of course, if you pay attention here, you should get all 8 of them. Now, there are 2 questions in Outcome 1. The first question is to do with the factor remainder theorem and its use in factorising polynomials. Although here, it'll be a fairly simple polynomial. It'll be a polynomial of degree 3, highest power will be 3, and the coefficient of that first term will just be a 1. The proper term for that is a monic polynomial. So for instance, you may have a polynomial of degree 3, which they will all be as far as this unit assessment is concerned. Not necessarily the case in an actual exam. They'll all be monic, so it'll just be one lot of the x cubed, and there'll be no trickery. All of the terms will be there. So that if it was power 3, you can have all 4 terms there, so there won't be any little bit to catch you out. Now, taking this as an example. There, some function of x is this polynomial of degree 3. What you're going to be required to do is factorise it given one of the factors, given a linear factor. Again, unlike in the exam, you won't be required to try and find that yourself. You'll be given one of the linear factors. So in this case here, the question would be, here's a polynomial. This x plus 3 is one of the factors. So the 2 parts of the question will be, first of all, show that that is in fact a factor, and then secondly, factorise it fully. So the first part would be, show that is a factor, and the second part will be, factorise fully. And this is for 5 of those 8 marks. So there's 5 marks available here. Now, there are 3 main techniques for factorising polynomials of this nature. There's carrying out an actual algebraic long division. There's forming a factorisation where you just have a template where you have unknown numbers in it, and then by equating coefficients, factorising it, that's called equating coefficients. Or there's synthetic division. Now, as far as this NAB is concerned, it's probably best just to concentrate on the synthetic division because it's the simplest. Now, that's where this factor remainder theorem comes in. The factor remainder theorem works this way. If this little linear term is a factor of some polynomial, if that is a factor, that means that if you evaluate that polynomial at the root of the factor, that should come to 0. And of course, if that is a factor, it means it divides inexactly. So this says if it's a factor, that means that the remainder is 0. And that's the factor remainder theorem. If the remainder is 0 on dividing by this linear term, then the value of the function evaluated at the root of that will also be 0. Which means you could show that that's a factor simply by putting whatever the root would be. Notice in this case it would be a negative 3 that would solve that, equal to 0. By putting negative 3 into this expression and showing that the answer is 0. But you don't need to do that because you can use that synthetic division table, where you put in the coefficients of each of the terms, paying attention that there aren't any missing terms, so you'd have to put in a 0. And then, in order to find whether or not that's a factor, you put in the root of that. In this case, it would be a negative 3. Now, what this table actually does, of course, is it's an evaluation table. You call it a synthetic division table because it does effectively carry out a division, but it's really an evaluation table. Putting that negative 3 through this table gives you the value of that expression at negative 3. It just so happens that the process of evaluating it produces these three coefficients here, which are the coefficients of the quotient, the number of times that that divides into it. But it is actually an evaluation table. You put -3 into this. Remember the way that this works. Start with that number, you just bring it down, then you multiply it up. That's one multiplication of that by that -3. You add it down, then you multiply it up. You add it down, and then you multiply it up. And of course that'll be a +6. Now notice that involved 3 multiplications of that by the 1. And then 2 multiplications of it by the 2. This is actually an evaluation table. And at the end, when you add it down, this says that the value of that function at -3 is 0. However, this also gives you exactly what you need to know for the division. That 0 would be the remainder, which means that that divided in exactly. So the first part would be this. For the 5 marks available here, 3 of them come, that's why it's handy just using this table, 3 of them come from setting this table out. The first mark is for realizing that it's the opposite of this, which is a -3, and that you're going to use the coefficients of the polynomial. So effectively, that's the first mark. The second mark is for going through all of this and producing this bottom line, all the way to the 0 at the end. And then the third mark, for showing it's a factor, isn't involved in boxing that off and just leaving that as an understood statement. The third mark is for making a statement which says, effectively, either the remainder is 0, so that's a factor, or the value of the function at -3 is 0, so that's a factor, using that factor remainder theorem. So whichever way you like, the third mark is for acknowledging that that 0 means something. So you can either say the remainder equals 0, which means x plus 3 is a factor, and that would get you the mark. Or because of the factor remainder theorem, you could say that for this part, the value of the function at -3 is 0, which means that x plus 3 is a factor. That's the first 3 marks. And then for the second 2 marks, it's just a case of saying, well, I already know one of the factors. That was that x plus 3. There must be a quadratic quotient, because the first times the first must gives an x cubed. There must be something starting x squared here, and these are the coefficients of that quadratic. It must be one lot of x squared, minus one lot of x, and then minus 2 for the number at the end. So f of x was actually equal to that. Notice you're not saying here equal to 0. This isn't an equation, this is factorising an expression. And for the last part, well, you're just on your own now. For the last part, it is finish off the factorizations. Now that doesn't necessarily need to factorise. It doesn't necessarily need to produce any real roots. However, for this question in the NAB, it will. So an x squared must be an x times an x. A 2 can only be a 1 times a 2. The centre term has got a negative, so the larger product must be negative, and that says they're opposite. So that would be it finished. So the third mark would be for this line, realising the quotient was made up from this part and stating it all, and the final mark is for setting it all out, but setting it all out, not just this little bit, putting all 3 together for the full factorisation. Don't be lazy and say, well, I've got that already, and then just put this part down. No, for fully factorising it completely. Those would get you your 5 marks. Now the second question is using the discriminant to find the nature of the roots of a quadratic equation. Again, the roots of an equation simply means the values of the variable that produce an answer of 0. Graphically, if I have a quadratic, then those roots would be the values of x, or the variable, that produce an answer of 0. In other words, the intersection with the axis. If it intersected, as in this case, twice, that means I've got 2 distinct real roots. If it was slightly higher than that, so it only just bounced off it, so it was a tangent, those 2 roots merge and become 1, but you still call them a pair of equal roots rather than just one root. And if this quadratic is higher still, well, there wouldn't be any intersection with the axis. There wouldn't be any real roots. As it turns out, there are other types of roots, imaginary roots. But as far as this is concerned, you would say there's no real roots. That's important. You wouldn't just say there's no roots, there's no real roots. And of course, these answers to the equation equal to 0 come from the quadratic formula, where those coefficients are the coefficients in order of the quadratic. The a for the x squared, the b for the x, and the c for the constant on its own. And there's a few things you can see here. There's a symmetry to the quadratic. That's the plus or minus part. You could almost split this into negative b upon 2a plus or minus the square root of b squared minus 4ac over 2a. And that negative b over 2a would of course stand for the centre line of it, and then the roots are placed equally on either side of it by this amount. However, that's not the purpose of this question. The purpose of this question is, how many roots would you get? Well, plus or minus. If there is a plus something and a minus something, you'll get 2. If there's a 0 there, well, it'll be a plus or minus 0, there would just be 1. And if for some reason this couldn't be worked out, and the reason would be you tried to find the square root of a negative, then you wouldn't have any real roots. And that's what you're using here. You're going to find the discriminant, which is this critical little part inside the square root. That determines how many answers you'll get, whether it'll be plus or minus for 2, or plus or minus 0, or just none at all. So as an example, if this were the quadratic, now again, there was 5 marks for the previous question, so there's 3 marks for this. Now there's 3 marks here. What's the nature of the roots of this? Or graphically, if you were to draw that, which of these 3 situations would apply to it? Well, the first step is to realise the only part that matters is this part inside the square root is the discriminant. So if you start off straight away by saying b squared minus 4ac, that gets you a mark straight away. Stating b squared minus 4ac is the first mark. Maybe we'll just move that out of the way. And then put in the values. So I'll just put that wee dot up here. Now when you put in the values, you need to put them in carefully. Make sure you do exact substitutions for it. So that in this case, b, being the coefficient of x, is actually negative 4. Now, I know that if you square a negative or square a positive, it gives the same answer. So effectively, if I was doing that calculation quickly, I would just think, well, that's the same as 4 squared. But not here. Make sure you write negative 4 squared minus 4 times. It's always handy to use brackets for the individual parts of the products, especially later on in a real question, where you've got algebraic expressions instead of just simple little integers. 4 times the coefficient of the first term, times c, which is the absolute coefficient, the number at the end. Now that's worth the second mark. Oops. Or rather, once it's been evaluated. So you have to write this out, being careful of this. If you don't do that, you'll lose that second mark. Evaluating that actually gives me a 16 minus a 16, which gives me a 0. Evaluating it gives me the second mark, so that's nothing then really, is it? And then the final mark is for making the statement. What is the nature of the roots? Which of these situations apply? Have I got 2 distinct real roots? Have I got a pair of equal roots? Or have I got no real roots? If it were the case where there was no real roots, make sure you don't just write no roots, or you won't get this third mark. You'd have to write no real roots. In this particular case here though, instead of 2 distinct real roots, I've got a pair of equal roots. So you could say the nature of the roots here is a pair of equal roots. Now the thing about the equal roots is they are real. It's just the nature of it. If you've got a real quadratic, then equal roots are real. You could always put in real just for safety, but you shouldn't really need to. A pair of equal roots. Oh, what? I'll just put in real roots, just for a bit of safety. This part here then gives you the third mark. Right, try these 2 questions yourself then to see if you'll get 8 out of 8. So, 5 marks available here. How would I set this out? First of all, I'd just set out my synthetic division. Coefficients 1, -3, -4, 12. Showing that x minus 2 is a factor means that 2 would be a root of that. So I'm checking if 2 is a root of the whole thing. So I'm going to put down my synthetic division, which really is an evaluation. My synthetic division table. That's the first mark. Going through it will give me the second mark. Add down, multiply up. Add down, multiply up. 2 times -1 is -2. Add down -6, multiply up. 2 times -6, -12. Add down, and I'll just separate that away, not that that's worth a mark. That's now worth 2 marks. 1 mark for this first line, 1 mark for this bottom line, and then for part 1, I would then state either, since the remainder is 0, x minus 2 is a factor, or the value of the function of 2 is 0, which by the remainder theorem means the remainder on division is 0. F of 2 is 0, which means x minus 2 is a factor. Might as well finish off of f of x. That's the third mark. Second part, for the remaining 2 marks, fully factorise it. Now it says fully factorise, not just carry on and finish off this little bit. So maybe I'll put it down fully. F of x is x cubed minus 3x squared minus 4x plus 12. I already know I've got x minus 2 as a factor, and this gives me the coefficients of the quotient, the number of times it divides in, 1 lot of x squared minus 1 lot of x minus 6. That's the next mark, up to 4 marks now. And lastly, finish off that little quadratic yourself. X squared must be xx, 6, that'll be a 2, 3, to give a difference of 1, and the middle term's negative, the larger one gets the negative, and that's the opposite. And there it is, 5 out of 5. So, question 2 then, for the remaining 3 marks out of the 8, what are the nature of the roots of this equation? Well, discriminant. B squared minus 4ac, and as soon as you've written that, there's my first mark, equals, now a careful substitution of exactly what these a, b and c's are, these coefficients are. B is actually a -7, so don't be lazy and write 7 squared, even though 7 squared and -7 squared gives the same answer. -7 squared, or you'll lose that mark. Minus 4 times the coefficient of the first term, times the coefficient of the last term, which is also a negative. That's going to give me a 49, a positive 49, plus, and that's going to be 12 sixes or 72, which altogether gives me 121. That's the second mark. And the final marks for saying, well, what does that mean? Well, if the discriminant is positive, that means in the quadratic formula, -b plus or minus the square root of over 2a, that is the discriminant, the bit that goes in here. I'll have a plus something and a minus something to separate it into 2 answers. So the final part is, then I've got 2 real roots which are separate from each other, so 2 distinct real roots is what I should put down. Put it all down. That in fact isn't all that could be put down. You could describe it even more than that, but as far as the NAB is concerned, that does. Because that's a positive number, maybe I should make a wee statement here. B squared minus 4ac is greater than 0, which means I've got 2 distinct real roots, setting it all out. But actually in this case, but those are the 3 marks, there is another mark that could have been available if they'd wanted it. And that's the case here where I've got the discriminant's positive, yep, so I've got 2 answers. Yep, so I've got 2 answers, so it will in fact cross where however it crosses. I will have my 2 distinct answers. But those answers will be nice answers, because that's a perfect square. So I'll no longer have a square root floating about in my roots for x. I'll have 2 nice answers, so that would make them rational answers rather than irrational answers. You could go further than that if you wanted, but you won't get any marks for that. You could say you've got 2 distinct real and rational, opposed to the cases where the discriminant isn't a perfect square, in which case I'd say irrational. You could put that in, but it doesn't get any extra marks. Another thing is, if you've got rational roots, if the discriminant is a perfect square, it means that your original quadratic would have factorised nicely into integers, rather than having to resort to the quadratic formula to find the roots. But I'm going over the top here. No, there've only 3 marks here. First mark, make sure you've stated b squared minus 4ac for discriminant. You could even write discriminant first. Make sure you've got the exact substitutions, including the signs, even though, of course, they don't affect the answer. That's the second mark. And then the appropriate statement. How many roots are there? There you go, 8 out of 8.